Welcome to this session on process management. In this particular session, we are going to talk about the basic concepts pertaining to the process. Before beginning the process, we would try to define what a program is, and then we will see that what is the difference between program and process. We will see how the processes can be characterized, and we will see that how a computing system can be modeled with the help of a process state transition diagrams. We will discuss starting with a two state process transition diagram. Then we will extend it to a 3-state process transition, then extend it to a 5-state process transition. Finally, we will see a 7-state process transition diagram, which is the model which is predominantly used in most of the current day systems. So let us begin with defining that what a program is. So we can see that a program is a set of logically arranged instruction to perform a specific task. Now usually the program is going to be written in some kind of a language. The language could be most of the time the language would be a high level language like C or Pascal, Fortran or C++. Then the program which is written in these languages are compiled to produce what we call as a machine executable code, which can be executed on a processor. And we should understand one thing, that is, a program is a sort of a passive entity. It usually contains a list of instructions which are stored on the and the program is stored on the disk, and we have seen that a program cannot be executed until unless it is brought in the main memory. That's the reason that program would require to be loaded into the main memory. So the question arises, how the program is going to get loaded into the main memory. Usually the program would get loaded into the main memory whenever the user would want to execute the program. And how user would want to execute the program? There are two ways in which the user can execute a program. The number one, if if the operating system is supporting a command line interface, then at a command line prompt the user types in the program name and then presses enter. For an example, it could be a abc.exe. So you type abc and press enter, or a.out. So you type a and press enter and you execute the command. The other way is where the graphical user interface is there, where the application is depicted in terms of icons. So double clicking on the icon would make the program to get loaded into the memory. Once the program gets loaded into the memory, we have a processor which will execute the program. So processor in general sequentially executes the instruction. Processor goes through a cycle of fetching the instruction, then decoding that what operation that instruction is required to perform, and then finally executing. And this fetch, decode, execution cycle continues and the processor is able to execute the program. So we need to define, so this is a basic characteristic of a program and how a program gets loaded into the memory and how it gets executed. While a program starts executing in the memory, so when program is getting executed in the memory, the microprocessor would fetch the instruction. After fetching, it will decode, and after decoding, if the requirement is there, it might even fetch a operand. This operand it will try to keep it in a register, and then probably after performing the computation, the result also would be stored in the register. And So we can very clearly see that when the program is executing, there is going to be a there are going to be a set of registers whose values are dynamically going to be changing as the program will keep getting executed. So while program is in execution, there is an additional information which gets created, which comes into the existence, and we call such a thing as a context of the program. And we say when a program is executing, we say an instance of executing program, we give it a specific name and we call it a process. So there is, the process is an instance of executing program, and there is a context associated with the process, and process is usually characterized by the code, also known as a text section of the program. Then process would operate on some data. So there is a data section, then process might call a certain set of functions, so it would have a system stack, and process also has a memory which we call as a heap. So the program process while job while executing the program might require more memory, so the memory is usually dynamically allocated from the heap. And in addition to this, there is a register. So all these things put together, they form a context of a process, and process is characterized by these things. In process, usually the process in the memory is going to be depicted in this particular manner. So we find that there is a text section, that is a program part. There is a data which the program instructions would access, and then there is a stack, and then there is a heap. Any allocation, a heap can keep growing as more and more memory keeps getting allocated, the heap can grow, or a stack can also grow. So this is how a process in memory is going to be depicted. How the process is created? So usually the process is created when a new job is submitted. Whenever a user wants to execute a new job, a process will get created. When a user attempts to do a login into the system, then also certain processes will get created. Processes are also created by the operating system to provide services. For an example, a program may request a read from the desk, or may request print. So these services, these reading, printing, etc., they are offered as a services from the operating system, and to provide these services, operating system might create a process which will offer these services. At time, we would also find that while a user program is executing, it is also possible that the user itself can create a new process. So user process itself can create a new process. So we say that process can be spawned by existing executing process. Let us see the order in. Let us see how a program or job is executed. So for executing a job, OS first needs to create a data structure for holding the context of a process. We had just seen that while a process is in execution, it has a context. So OS would need to create a data structure where the information about the context and about the context can be stored. So that is the first job. Process would create a data structure where it can hold the context of a process. Once this job is over, then as and when the memory becomes available, the process could load, the process could be loaded into the memory. This job can be loaded into the memory. Once the job is loaded into the memory, Now we can assume that there can be a many jobs loaded into the memory. So at some point of a time, one of the job which is loaded into the memory is going to be picked up by the scheduler, and scheduler will schedule this job on a processor for the purpose of execution. And once a job is scheduled on the processor, the job starts executing. The process which picks up the job and schedules it on a processor is known as a dispatcher. So we find that dispatcher is the process which will pick up a job from the memory and it will dispatch it to the CPU. So dispatcher process, the function of a dispatcher process is that it dispatches the ready to execute processes for the purpose of for the execution. And when such a thing would occur, so it can dispatcher would get invoked at several instances. 3 of the instances are listed here. One of the instances that once the currently executing process terminates, that is it finishes its execution, so a new process would require to execute for operating system would always try to keep the CPU busy. So for the maximum utilization of a CPU, as soon as the one process which is currently executing it terminates, the OS would try to schedule the another process. So dispatcher process would dispatch another process. So this is a first case. In a second case, it may happen that the executing process is allocated a small chunk of a time for its execution. So when the time slice allocated time slice expires, new job could be dispatched, or another thing could be that the executing process would make an IO request, and after making the IO request, this particular process gets blocked. So this is the case when again dispatcher would get invoked and it will dispatch a new process. And we should note one thing, that dispatcher is a system process which is a part of a operating system. Let us understand a bit of things pertaining to the process with respect to the multiprogramming. This is just to re-emphasize the concept of multiprogramming. In multiprogramming environment, we find that we know that many jobs can be there in a memory, and at any given point of a time only one of the job is going to be executing. We also know that multiprogramming is valid for the system with the single CPU. That is, multiprogramming is the word used in conjunction with uniprocessor systems. We know that all the jobs which are there in the memory, they are ready to execute. So at any given point of a time, we can very clearly see that job could be in 2 states. There can be a set of jobs which are there in a memory and they are ready to execute, and there would be one job which would be running. So we can say that the jobs are going to be in 2 states, one in a running state, and other there would be a set of jobs which will not be in running state. Once again we try to see the memory layout in case of a multiprogramming environment. So we find that we have a dispatcher process, and then we have 3 processes. Let us assume process A, process B, process C, and currently the process C is executing. So how the things happen here is that once the process C execution is carried out with the help of what we call as a program counter. Program counter or a instruction pointer is a register which is a special purpose register available with microprocessors, and this registers point to the instructions which is going to be executed next. So with the help of a program counter, the processor would be able to execute instruction one by one sequentially. let's say that a process C gets over. So, whenever the process C will get over, now what would happen, that dispatcher is going to get invoked, and out of remaining say process A and B, now dispatcher would choose one of the process and it will dispatch. So, that particular process would begin executing. So, after the completion of a process, dispatcher is going to execute to schedule to dispatch another available process to the CPU. So, again let us just see here with the help of a kind of a Gantt chart, that how the dispatcher process and the user processes are executing. So, in this particular example, we have taken 3 processes, P1, P2, P3. These are the user processes, and D is the dispatcher process. And D, since dispatcher process has to pick up a job and execute that job, dispatch it to the processor, it is said that it is going to take a constant amount of time. So, we find that in the beginning, when let us assume there is a scenario where processor is free, and these are the 3 processes which are there in a ready state, ready to be executed. So, dispatcher would run first. So, dispatcher runs and what it does, it from the list of 3 processes, it picks up the P1 process and dispatches it for the purpose of execution. So, P1 executes for this much period of time, is starting at this point, it executes up to this point. At this point, P1 terminates. So, once again now dispatcher is invoked, and it picks up now P2 from the 2 remaining processes, and it dispatches P2, and then third, once the P2 is over, then we can see once again that the dispatcher gets executed, and it executes the P3. So, we find that after executing of every process, the dispatcher is going to execute. So, if we try to find out the total time to execute these 3 processes, so the time taken to execute these 3 processes is going to be P1 plus P2 plus P3 plus 3 times the time taken by dispatcher. So, that is the total time which is going to be taking to execute these 3 processes. We can clearly see that if the value of D is very large, then the overhead for executing the user program is going to be very large. So, that is the reason it is required, it is a requirement on the OS designer to design the dispatcher to be very efficient, so that it takes a minimal amount of time. So, we can see clearly that from such kind of a thing, the design requirements would arise, various design requirement for a OS is going to arise. Let us see that we have seen that what a process is, and from the system perspective, we have seen that in a multi-programming environment, there can be a lot of processes which are there going to be in the memory, and so it would not be wrong to say that a multi-programming system is an assemblage of a set of processes, and these processes can be of a 2 category. They can be of 2 category. One, that is, they can be a user processes, that is pertaining to the job which is user application, and there can be a system process. For an example, a dispatcher. Dispatcher is one of the process which we have known. It is a system process, and we can again visualize that at a given instance of a time, the processes can be in different states. Right now, we know that processes probably can be in 2 states, that is executing a state and not executing a state, running a state or not running a state. And since we say that the processes can be in a different state, so from this we will see in a coming time that the system itself can be modeled with the help of what we call as a state transition diagram. So we will begin and we will try to first explore a very simple model, that is a two-state model, and then we will keep extending and we will see that see the various other models. So let us see that let us begin and start exploring that how the two-state model functions. So in this case what we are saying is that the process can be in the two states, and the states are either the process is running or process is not running. So whenever a new process is started, it will enter into a state which is a not running state, and then this not running process at some instance of a time, at some point of a time, dispatcher will get activated, and dispatcher will pick up one of the not running process and it will dispatch it to the CPU, and it will come into the, it will transit into what we call as a running state. And so on the CPU this process would execute for some period of time, and it is possible that process would complete its execution. So when it completes its execution, it will follow a path, that is, it will exit from the system, it will go out of a system. There are chances that while this process was executing, process might request for the service, IO service, and it might get blocked. So it will, once it gets blocked, it will go to a what we call as a not running state. So now this is how from a running state a process might move to the not running state. This is a one case, this is a one scenario, that a process requesting for a IO device, IO services, that is the reason it is going to get blocked and it is moving to the not running state. There can be several other scenarios. The other scenario can be that the executing process, its time slice expires, the time allocated to this particular job expires. So and the job is yet not over, job has yet not finished, and that is the reason this particular process would once again move from running state to not running state and wait for its turn when it will once again get scheduled and it will get its execution completed. So the same state transition diagram here we are trying to show with the help of queuing diagram. So in queuing diagram we can see that we are maintaining here a queue, and this is a queue which we can say is a not running. This queue is depicting the set of processes which are not in a state of not running, and then the processor is the one which is where the processes are executing. So any process which is there on the processor is in a running state. So this particular diagram shows that we have a process P0 running on a processor, and we have a process P1, P2, P3. They are there in the memory and they are there in the queue, and they are waiting for their turn to be dispatched. So at some point of a time these processes are going to get dispatched to the processor, and after executing on the processor either it can exit or it can return back and join the queue once again. So so we have seen that the return path, we should see that there are two conditions in which the process would return back to the queue. The one, when it makes a IO service request, or two, when time slice for the executing process expires. So the second case is a simple case where the time slice expires, so it comes and joins. This will again wait for its turn to be serviced again, whereas the first case is a more complicated case where a process has made a service request. It is waiting for, let us say that it made a IO request, it made a request for reading a file from a disk. So, it is possible that the disk would usually take some amount of a time to get the data and deliver it to the process. So, during this period of a time, till the time the data is made available, that particular process cannot be executed, it would need to wait. So, we can very clearly see that it is possible that at any given point of a time, the set of processes which are there in the queue, they could be of two different category. One, they are ready to execute. The second category would be the processes which are actually blocked and waiting for the services to be completed, and those blocked processes cannot be allowed to execute. So, in such a scenario, when the queue is going to have two different types of processes, now the responsibility of a dispatcher would be to linearly search the queue and find out the process which is ready to execute. And it is possible that let us assume there is a case that the P1 process is the one which is blocked. So, now when the dispatcher comes, dispatcher cannot just simply pick up the P1 and dispatch it, because P1 is blocked and it is waiting for the services to be made available. So, what it would need to do is it will leave the P1, it will go to P2 and check that what is the status of a P2, whether P2 is blocked on a services or not. If P2 is also blocked, then it will move on to the next, that is a P3, and hopefully it will eventually find out a process which is ready to be executed. So this is a problem which is, so we would find that our dispatcher would be required to make a linear search and it would take more time, and as we just a while ago we said that dispatcher has to be really very efficient. So, we cannot allow the dispatcher to take a variable amount of a time, because if linear search has to be carried out, the amount of a time taken to find an entry is going to be dependent on the number of element in the queue. So, whereas we said that dispatcher is going to take a constant amount of time. So, we cannot allow such kind of a algorithm to be used by the dispatcher. So, the question arises, how do we solve this particular problem? So, this problem is primarily for the reason that the queue which we are maintaining has two processes, one process which is ready to execute and the process which is blocked. The two states which are indicated in the state transition diagram, we find that we have a not running, the transition to state transition, not running to running state transition. So, we find not running to running state transition would occur under these conditions, that process in a running state finishes its execution, or process makes an IO request, or a time slice for executing process expires. So, whenever the time slice for executing process expires, what happens, that a process which is existing in the not running state, one of the process which is there in a not running state will be shifted to the running state. And the second transition which we have seen is a running to not running state occurs when a running process makes an IO request or time slice of executing process expires. So just now we have seen that in a queuing diagram that we had in the diagram that we had a dispatcher. So, dispatcher usually schedules a ready process to a CPU for a execution, and in case of a two state model, we have just discussed and found out that not running state contains processes which are ready to run and which are in a blocked state. So this is the main cause, because dispatcher would need to discrete. So, we said that if suppose we can break the not running state, split the not running state into two states, and the one of the state can be a ready state and the other state can be a blocked state. So let us see that if we try to do such kind of a thing, then what kind of a state transition diagram we will get. So the not running state, as discussed, we have now split into a two states, one being a ready state and other being a blocked state. So now let us see that how this three state model is going to work. So a process is going to be whenever a process new process is required to be executed, it is admitted into a ready state, and from the ready state it will be dispatched by a dispatcher in the running state, and from the running state, if the time slice of the process expires, it will return back to the ready state, or if the it's a execution of the running process gets over, then it gets released. The third possibility is that this running process might make a service request and it goes and gets blocked on the service. So once the service gets completed, the event occurs for which the process was blocked, and process can move from a blocked state to the ready state. So in this three state model, we can see that we have three states: the running state, the process is, that is running state specifies the process that is currently being executed. Ready, it specifies a set of processes that are there in the memory and they are ready to be executed, and the blocked state signifies that a set of processes which are blocked for some kind of a service from the operating system or some kind of a IO, they are blocked on some kind of a IO request. And usually we find that the processes which are in a blocked state, they are unblocked by occurrence of an event, and this event is usually indicated with the help of an interrupt signal. So for an example, it is something like this, that let us say that OS would make a request to the hard disk for reading the block of data from the hard disk. Now hard disk controller will read the data, and after reading the data it will try to give this data to the OS. Once the hard disk is ready with the data, what it does, once the hard disk is ready with the data and it has transferred that data in a specified memory location, what it does, it tells the operating system by generating an interrupt signal saying that the job has been successfully completed. So this is how the most of the time the IO services are going to be handled. So again, a three state process transition diagram. Let us try to look in terms of a queuing diagram. So in a two state process transition diagram, we had seen that we had a one queue, there was only one queue, and there was a processor. In this case, we should see that we have a one queue in the beginning where a new processes are coming and entering, or the set of processes which are pausing are, so that is a one queue. We have another queue which hold the set of processes which are in blocked states. So my queue, this particular queue is a queue which is corresponding to a ready state, and this queue is a queue which is corresponding to blocked state. And in both these queues can have a multiple processes. The previous diagram, we had seen that in this particular diagram we should see one specific issue here, that we have a queue which is a blocked queue, and this blocked queue would have processes which are waiting for different devices. It is possible that there can be a process which is waiting for a hard disk, there can be a set of processes which are waiting for a printer, there can be a set of processes which are waiting for a network. So whenever an event occurs, then it is required that one would need to scan through the queue and find out the process, appropriate process, and for unblocking, and one would require to scan through the complete queue. So for this reason, it was proposed. It is proposed and it is adopted in many of the operating systems that instead of maintaining a single queue for keeping track of all the blocked process, maintain individual queue for the individual devices. So there can be a system which will have as many queues as the number of devices are going to be there. So this is indicated with the help of a fresh diagram. So we find that here we are indicating that we may have a n number of a queue, Q1, Q2, Qn, where each of the queue is for a different event, or in terms we can say it is meant for a different IO device. So we find that we had seen a 3-state model. Now let us try to look at a 5-state model. In case of a 5-state model, these 3 states are there. These are the states which we have already seen. Now we would try to see that why two new, we are adding a state which we are calling a new state, and we are adding a state which we are calling a exit state. So we will try to see that why these states are required. So let us see that why do we require a state named as a new state. So we know that whenever a job is submitted, what OS does, OS creates a data structure for keeping track of the process context, and it is possible that it creates a basic data structure where it will keep a track of where the text section of a memory for the process is going to be there, where the data section of a memory for the process is there. So all these information it needs to maintain. And what happens that at the time, so a basic data structure containing the information is there, the actual program would require to be loaded into the memory, and it is possible that when the job is submitted at that point of a time, the memory may not be available. So that is the reason that under such a condition, then what do? User submits a job and the system might just throw a message saying that insufficient memory and program cannot be executed. So now what would happen, that the user would require to keep trying, and probably once in a while when he becomes lucky, his program will get executed. So rather than handling things in this particular manner, it was thought that let us create a state where we have a basic data structure where the process information would get stored, and once the memory gets allocated, once the memory becomes available, then what happened, that the entire process will get loaded into the memory. So that is the reason that a new state was an additional state created. And please remember that a process, when it is in new state, the entire process is not in memory. The process, the text section, data section and its context is still on the hard disk. And there are at times, see, this is a one scenario in which the new is needed. The another scenario that it is possible that at times the operating system may say that more than 5 or more than n number of processes should not be there in the system for the efficient execution or efficient utilization of a system. So, the operating system itself puts a limit on the maximum number of the processes that can be in a ready state. So, for that reason also it is one can see that one would require to have an additional state, that is a new state. The various valid state transitions. So, in the above mentioned in the diagram shown earlier, we find that these are the valid state transitions, new to ready. Then we have a ready to running state whenever executing process either completes its execution or it goes and makes a IO request, then a new process is to be executed. So, the process would move from a ready to running state, and a process running to exit occurs when in the case when process executing on a processor completes its job. So, it goes to the exit and then running to ready. So, this movement essentially occurs when the running time process which is running its time slice expires. So, it moves to the ready queue, and running to blocked state would occur in a case when a process which is running, which is executing a program, and then it makes a IO request. So, it goes into a blocked state, and whenever the event for which the process is blocked occurs. So, once the event occurs, the blocked process would move to a ready state, and any process, please note that any process can go to the exit state from any state. Let us look at a scenario. So, we have seen that how a 5-state process transition diagram would work. The question here is that is the 5-state process transition diagram is enough to handle all the cases? So, the obvious answer here is that no, it is this particular 5-state transition model would not be able to handle certain scenarios. Let us consider one of the scenario. So, here what we are saying that we have a set of processes which are, let us assume that we have a set of processes which are in a ready state, and these processes they go and they are scheduled on a these processes they are scheduled on the processor. Dispatcher dispatches them one by one to the processor, and while executing for a very small amount of a time on the processor, each of these processes, what they do, they go and get blocked onto the IO device. They make a IO request and they get blocked onto the IO device. So, there can be a scenario where all the processes are blocked on a IO and ready queue is empty. So, logically speaking, to maximize the CPU utilization, the attempt should be made to bring in a process from a new state to the ready state. But we find that if when we try to move a process which is there in a new state to the ready state, we find that there is no memory which is available. All the memory is consumed by the processes which are in the blocked state. So, the question arises, then in this case we can very clearly see that until unless one of the blocked process gets unblocked and starts executing and finishes its execution, memory is not going to become available, and hence new processes cannot be brought in. So, this would lead to some kind of a underutilization of the CPU. So, the question which is in fact is not acceptable. We as a OS designer, one would want to maximize the CPU utilization. So, the question is that how do we handle such a situation? So, to handle such a situation, what was suggested was was a technique, that is a swapping. So, in case of a swapping, what is done is that a blocked process which is waiting for some resources, some IO services to be completed, is swapped out of memory. That is, it is taken out from the main memory and put on the hard disk to create a memory. So, whenever such a thing is done, we call a process has been swapped out from a main memory to the hard disk. When we say swapping in terms means that removing something from a main memory and putting it back onto the backing store. So let us try to create. So we find that what we need to do is we need to swap out a process. So now we have a process which is blocked and which is not in memory. So we create an additional state and we call it as a suspend state. So the diagram shown here is, now you can see that it is having 6 states, 1, 2, 3, 4, 5, 6. That is, new is a new. We have a 6 states here. Let us try to analyze that how the things would work here. We have seen a 5-state transition diagram. We understand that how the transitions they would occur, what are the valid transitions. Now in this case, in this particular model, the one additional state, that is a suspended state. So what happened, that we have a set of processes which are in a blocked state. Now we choose, operating system chooses one of the process and it swaps it out, it puts it onto the hard disk. So, and we call this state as a suspended state. Please note that the process which is in the suspended state, its characteristic is that it has made a request for IO service and it is still waiting for the service to be completed. The second point is that this process is not in memory. So we should clearly distinguish between the process which is in a blocked state and a process which is in suspended state. The process which is in blocked state is in memory and it is waiting for services, whereas process in suspended state is waiting for services and it is not in memory. So process in suspended and process in blocked state, both of them are waiting for some services. So as soon as the event occurs, as soon as the service becomes available, the process which is in a blocked state can very easily move to the ready state because it was in memory, only the state change is required to be done. Whereas the process which is there in a suspended state, when the event occurs, if we try to send it to the ready state, that would essentially mean that the additional memory is required to be made available, because the process which is in suspended state is not in memory, and you would need to activate, when you wish to activate this suspended process to a ready state, that would require that the memory should become available. And it is quite possible that when the event occurs, at that point of a time the memory is not available. So if the memory is not available, you cannot move the process from a suspended state to a ready state. So this particular 6-state model, we can clearly see that it is not going to serve the purpose. So to overcome this, we create a model which is going to be a 7-state model. So the suspended state in a previous diagram is now divided into a 2-state. We call it as a blocked suspended, that is a process which is in blocked state waiting for a services and not in memory, and then we create another state, ready suspended. Ready suspended is a kind of a thing where the process is not waiting for services. It has got its service, it was in blocked state and it was waiting for an event to occur. When the event occurs, the process moves from a blocked suspended state to the ready suspended state. So, ready suspended state is characterized, can be characterized by the fact that the process is in memory and it is not waiting for any services. Ready suspended state is characterized, can be characterized by the fact that process is not in memory and it is not waiting for any services. So, as and when the memory becomes available, the ready suspended process can be moved to ready state. We can clearly see here that the new state and the ready suspended state are one and same. So one can one can merge new and ready suspended state together and say that they are one and same. So let us just try to see that what are the various state transitions which are what are the various valid transitions which are possible here. So we can say that we can clearly see that ready process can move to the running and running to a blocked, blocked to blocked suspended or blocked suspended to blocked. So we can clearly see that what are the possible state transitions which can occur. So here we try to describe that under what conditions what transitions would occur. So the first case, that is a blocked to blocked suspended. So if a ready queue is empty and we find that there is a insufficient memory which is available, then one of the blocked process can be swapped out. And in other scenario when such a thing can happen is that if currently running process requires more memory and the OS finds that there is no more memory available in the system which it could allocate to the currently executing process, then it may decide to suspend one of the blocked process to a blocked suspended state. Blocked suspended to a ready suspended. So whenever the event would occur, the process would move from a blocked suspended to the ready suspended. Please note one point here, that the process which is in a blocked suspended state is not in memory, whereas the IO device is trying to provide the service. So the OS would need to know that which process is there in which particular state, and including the set of processes which are in a blocked suspended state, even though this process is not in the memory, but OS would need to maintain the information about suspended processes. Ready suspended to a ready. So if ready queue is empty, then the processes can be moved from ready suspended to a ready. The process can also move from a ready to ready suspend, though normally what actually what is a preferred thing is that one would wish to swap out a blocked process, because blocked process is the one which is waiting for some services. It is currently even if the CPU is idle, this blocked process cannot be executed. So under the normal circumstances, a blocked process should be suspended, but sometimes it may also happen that if it may happen that there are no blocked processes, but there are only ready processes and executing process. Then in that case, if the more memory is required to be created, then this is the only means of creating a more memory, that one can swap out a ready process onto the hard disk. Block suspended to a blocked can occur if while the system is waiting for a event occurrence. If more memory becomes available, then it is possible that a blocked process could be could be moved to the blocked state. Running to ready suspend can occur, that currently executing process can be directly sent to the ready suspend, and to exit a state we can move from any state. From any of the state one can move to the exit state. Thank you.